Hi everyone, today we will start with Module 2, Foundations of Physics. We will be covering the first part of Module 2, which is physical quantities and units in today's lesson. The aim of Module 2 is to look through the foundations of physics. So what we are aiming to get through is the basic understanding of what we mean by physical quantities, what we mean by SI units, derived units, and how we use all of this very basic important stuff in physics. First thing I will start with is physical quantities. The reason why this chapter is very important before I start is the fact that we need to have a common language in physics, in engineering, and any other science for that regards. Due to the fact that obviously you already know from the periodic table that everyone uses the same symbols in the periodic table, and scientists, for example, in Japan should be able to communicate with scientists in Britain. They have to use the same common physical units and quantities and be able to understand each other's work through that common language. As you might already know, a lot of the research done in one country doesn't just involve the same country scientists. So in the UK, you don't just have British scientists working on a project, you have scientists from all over the world. So a common language is a very important part, hence why this is one of the first two modules that are very important before you start your course, just to get the basic foundations of how you can communicate throughout the course. Okay, so first things first, what is a quantity? It's just simply a measurement of something. Now all physical quantities have a value, a numerical value, and a unit. For example, when you're driving a car, I know in the UK the speed limit is given in miles per hour. Some other countries have it in kilometers per hour. And when we talk about someone running, we usually use meters per second as a unit. But the idea is that it has to have a number. So for example, if I say I'm driving at 20 miles per hour, so you have your numerical value, which is a number, numerical number, value, and a unit, miles per hour. Obviously, this is not the same as 20 kilometers per hour, and we'll get to that later on. Another thing that I could say is that, for example, I run 5 what? 5 meters, 5 miles, or 5 kilometers. So as you can see, the distance is the quantity that I'm measuring. And by saying 5 doesn't have any meaning. It's just a value. So for it to be a physical quantity, it needs to come with a unit. And obviously, meters, miles, and kilometers are very different. So that's the biggest importance of us constantly labeling our numerical values with our physical quantities that have a value with a unit. Otherwise, it has no significance at all. So in the second part, it asks you to be able to apply the knowledge and understanding of making estimates of physical quantities listed in this specification. Now, the important part is, what are estimates? So estimates are like a simple substitute that you can do to perform a calculation. There's different ways of looking at it as well. It's not just one thing. For example, if you have a calculation that involves, multiplying, getting the cross-sectional area of something that's 57 meters long times, for example, 11 meters high or something. Now, sometimes when they ask you to make an estimate, you can round your answers to one significant figure, which will leave you to 60 times 10. And then you will end up with 600 meters squared. Now, if you do the calculation with a calculator, the answer comes up to 627 meters squared. The key word is if the question asks you to make an estimate. If it doesn't ask you to make an estimate, it tells you to calculate, then you have to use your calculator. If it's an estimate, you have to round it. Another example of estimating is, for example, if you're told to calculate the volume of an apple or a banana. So for the apple, you can use the volume of a sphere, and through your own personal knowledge and obviously owning a ruler, you can approximate the radius of the sphere of the apple, and you can make a simple calculation by estimating that the apple is quite similar to a sphere, or that a banana, like a medium length banana, is approximately a cylinder. So you can get the volume of a cylinder. So estimates involve making simple, educated guess to get an answer, even though it's not going to be the same and equally the same value, like in this case, it's like the exact same value, but it's quite close to the real value. Obviously, estimations take place a lot in certain engineering fields, but obviously in not an extreme way. So estimations are very, very useful. So you say, why not calculate, why estimate? Sometimes estimations are very, very helpful, especially since they don't have such a huge error percentage. There's also another way of estimating, usually is with orders of magnitude. So for example, when we come across things like the mass of an electron, the real mass of an electron, and the mass of a proton and a neutron, we have to compare which one's bigger than the other one. We don't have to give the precise number. Sometimes we can just talk about how many orders of magnitude is bigger. One is bigger than the other. We'll see more examples of these throughout the course. That's why in the specification it says to make estimates of physical quantities listed in this specification. So this will be a constant building up throughout the course. It's just as long as you understand what we mean by an estimate and differentiate it from an actual calculation. Also, a good point to mention here is that not all physical quantities actually have a unit, and we will come across this in terms of calculation. So if I'm talking about the efficiency of something, it comes in percentage or in a decimal, that's less than 1. We're talking about magnification, it's in number, but this still should have a meaning in terms of the calculation and where it leads to. So some quantities are just numbers. So if I say 20 students, you don't have units. You are a quantity that I can measure, but not, you don't have a unit. So certain quantities do not have units, but most of them do, and the importance of mentioning the units is extreme. And this is where we come into 2.1.2, the SI units. Now, years ago, they came up with this system, which is very, very important, the international system of base units, base quantities and their units, sorry. Now, base quantities are what we consider very basic quantities that make up other measurements that we actually take. So let's start with going through one by one. And we're going to call these SI units for simplicity. We don't have to say Système International. The first one is mass, which is measured in kilograms or kg. Second one is length, which is measured in meters or lowercase m. Now, a very, very important part is the fact that we have a quantity. So the quantity is what we can measure, for example, mass, length, and etc. Then you have the base unit, so what we measure it in. So for mass is kilogram, for length is meters, for example, current, electric current is ampere, And then they have unit symbols. This is very important because you will need to represent every quantity with their unit symbol, unless you're asked what is the base unit of something. So usually when we write, when we do a calculation, we have to state the unit symbol next to the number and not the name of the unit, for example. Now, there's a very important part here. When we are using symbols for units that are named after a person, then the symbol has to be capital. If it's not named after a person, then it has to be lowercase. So for example, kilogram is not named after a person, so it has to all be lowercase letters. So kg. For length, it has to be meters in lowercase m because it's not named after a person, but current is named after a person, hence the unit symbol is capital A. We have time as well. Time is measured in seconds, which is lowercase s. This is not named after a person. I already mentioned current. Temperature is measured in Kelvin. It's named after a person, so it has to be capital K. And the amount of a substance is known as moles, or else in a shorter version, MOL, lowercase because it's not named after a person. There is also another extra base unit, a seventh base unit, that you do not need to know. And the other thing is that we won't come actually across the amount of substance moles until A2 content. So currently we're going to be doing AS content, and by the end of this year, well, of this academic year, you will come across the moles in mostly thermophysics. So you do need to know them either way. Doesn't matter if you come across it yet or not. But there is a seventh unit, SI unit, that you don't need to know for your course, but for those of you who are interested, it's the unit that we use for measuring luminous intensity, the candela. So the quantity is basic, the base quantity is the luminous intensity. The unit is called candela, and the symbol is lowercase cd. But like I said, this is not assessed in this course. It's only for those who are interested to know a little bit more. Why, though, do we have to use these symbols? Why these units? Why can't we not use centimeters or feet or stones for mass, or for temperature? Why can't we not use degrees Celsius? Why can't we not use hours for time? Well, it's very important because in calculations, if one set of scientists is using a specific unit, like for example, they're using pounds and feet for their measurement, another team is using kilometers and hours, another team is using meters and seconds. When they bring up together the whole research, things will not match, things will be hard to get around. And there's something that you can read into about when in 1998, when NASA launched the Mars Climate Orbiter, which cost hundreds of millions of pounds, and how different teams were working with different units, and that led to basically a big disaster, with a lot of that hundreds of millions going to, a big bang and getting destroyed just because they just assumed that they were using the same units. So it's very, very important to follow this system so your calculations come out right. So we go to the next point now, where we come across the derived units. I already spoke about base quantities and their units. Now we're going to talk about derived quantities and their units. Now, a derived quantity is just quantities that we can measure, like speed, force, pressure, energy, and so on, that have the different units, but all those units, so like for example, force has a unit in newtons, but those units are for the units of force are derived from base units, base quantities. Some of them do have special names, like for example, the unit for force is newtons. It has its own special name, but it's also, it can be expressed in SI units because it's made up of base quantities, like I already said before. So these are our base quantities, and everything else that we can measure is a combination of the base quantities in a different way. So either multiplication of them, a division of them. So for example, mass times meters divided by time gives you momentum, or mass divided by length to the power of 3 gives you density, and so on. So those are derived quantities. They, like momentum, density, they involve more than one base quantity in a different combination. And like I said already, you also have certain units that have their own unique symbol, like Newton, which I will show you in a second how to do as well. So we have a quick look. Speed is a derived quantity, is distance divided by time. So distance being a base quantity, time being a base quantity, like we saw on this section. But we also know that they have their own base units, SI units. So for example, distance is in meters and time is in seconds. So I end up with meters per second as my derived unit. And you can also, here is a nice hint, you can also always figure out what quantity you're talking about if you know that, okay, meters is distance, seconds is time, and you just work out the other way around the equation. So you figure out what you have, and you know that speed is distance divided by time. So if you ever feel stuck, if you get used to the units and everything, you can always work around it. Another quantity that you know is, for example, density or acceleration. Acceleration, if you remember from your earlier courses, acceleration is the change in velocity or speed. In this case, we're going to be using mostly velocity in this course because it becomes more, fancy. Not fancy, but more accurate. So we have velocity, we know is the same unit as speed. So that's meters per second divided by second. Now, this is a good point for me to mention here, that every time you see something like a unit like meters per second, for example, this is the same thing as writing meters per second. This is a mathematical notation that if you haven't learned yet, we'll go through more if you need more support on that. So then acceleration will have a derived unit of ms to the minus 2, so meters per second squared. So it's more preferable at A level to use this representation of your units instead of per second, because this makes it quite a bit messy when you start having more units under the division line. Okay, so now going to newtons. Why? Well, because we use newtons and everything a lot all the time, and because of the work and respect towards a certain scientist, certain, derived quantities got a special unit symbol, but it's still made up of SI units. It's just that out of respect, usually, of the person that was involved in the research or discovery, the name stuck around. I'll go through the Newton, then I'll go through pressure as well. I'll do a few examples just to get you a bit used to it. So force, can be calculated using mass times acceleration. All these equations will be given to you, so you're quite lucky for your A-level course. You just have to get used to your units, which is very, very important. Now, mass is a base quantity, which is has a unit of kilograms. And acceleration I already showed it to you here, but if you ever forget, you can go through quickly the equation, write it down, figure out the units. So the derived units of acceleration is meters per second squared. So the force we know the unit is newtons. So 1 Newton is actually is the same thing as saying 1 kilogram meter per second squared. So a Newton has its own name, which is exactly the same thing as me constantly saying, oh, 1 kilogram meter per second squared, instead of me saying 1 Newton. So it has its own unique name and unique symbol. And once again, because most of these unique named symbols come after people. So for example, Newton, Pascal, joule, watt, volt, ohms, coulombs, hertz, they're all named after people, so they all have to have a capital first letter. Like for example, Pascal's, so it's a pressure, measure pressure in pascals. Pressure is measured using the equation pressure, force divided by area. We already saw that, and since it's named after Pascal, it has a capital P but a lowercase a. I think Pascal and Hertz is the only ones that have 2 letters. So it's always capital, the first one, the second one lowercase. We know that force already, I said that it's in newtons, but I already showed how to get newtons in its base units. Well, it's a derived unit still, but being composed of the base units. So it's kilograms meters per second squared divided by the area, which is meters squared. So we end up having 1 Pascal is equal to 1 kilogram meter times meter to the minus 2 is going to leave us with meters to the minus 1, second to the minus 2, and that's what 1 Pascal is equal to. Okay, so if you notice here, it says to be able to apply knowledge and understanding of units listed in this specification. As I said already before, we will be coming across a lot of different units in the specification. You will get used to them, so this is going to be, again, something that we're constantly building upon. Now, checking the homogeneity of physical equations using SI base units. This is a very important part. I know this sounds like a fancy word. It is a bit. So homio means same. Genus, genos, is the same thing as kind. So basically the same kind. And in this case, when we are checking that it is the same kind of physical equation using SI base units, what we mean is that both sides, we can check that an equation is valid if both of the sides of the equation have the same SI base units. I will give you an example to show this, and you should be able to do it as well for exam questions. This actually carries a lot of marks in exam questions. So just to quickly re-summarize, an equation will be homogeneous only if the base units of all the quantities are the same on both sides of the equation. So we'll give a very good example. I'll give 2 examples. And also just to mention this here, this is very important, especially when people are deriving their own equations. If you make a mistake at the end, you can and you missed out a quantity in your equation, you can figure that out by using the quantities you have and basically working through their base units. So it's a very important part of physics, because you can always double check whether it is homogeneous or not. I'll take you through, for example, the equation for work done is equal to force times distance. So work done is the same thing as energy transferred, so please make sure that you do revise over your GCSE content. So work done is equal to force times distance. This equation will become a little bit more complicated in the A2 course, but don't worry too much about it. Still has the same idea behind it. It's just going to add angles to it, and that's what you're going to see later on. Now, I'm just going to write it with symbols. Work done is force times distance. S stands for displacement, by the way, which you're going to have to get used to as well, especially all the symbols. So now if I say, okay, what's the unit of work done? You all know that the units of work done or energy transferred is joules. We know that the unit for force is newtons, and we know that the unit for distance is meters. Now that doesn't look homogeneous yet, because obviously we're seeing joules, newtons and meters, even though joules is in newton meters. It doesn't mean anything yet until I break it down to the very SI base units. That's a very, very important part, because these are not SI units here. These are derived units. So I can start with, for example, for newtons, I already done it, so I'm not going to double do it again. I already derived it. The easiest way to derive the units for force is using force is equal to mass times acceleration, because we know that mass can give us the SI unit kilograms. I can also write acceleration in the SI units of meters per second squared. These are not derived units, these are base units. So far I know that joules, actually I'll do it step by step in a different way so it's easier. I would also suggest that you follow the same process in the exam, because it shows them clearly that you know what you're doing. So we said newtons here is given to me. So basically what you'll do, you will show this exact working out. So that will be kilograms meters per second squared. And obviously that's meters because it remains as meters. I'm just going to simplify this whole side of this equation as kilograms. Meters times meters is meters squared. Oh, I'll put another bracket, which I shouldn't have, because I'm just keeping everything now in the same bracket. Meters squared per second squared. So I turned force times distance into all of the SI base units that I needed. Now, when it comes to joules, I have to work through it in a different way. So we know that energy can be calculated. We know how to calculate gravitational potential energy. We know how to calculate kinetic energy. So let's use the equation for kinetic energy before I continue. So kinetic energy is a half mv squared. I know that the unit, and we know that kinetic energy is measured in joules. I don't know why I always make my line like that, but you understand. Half doesn't have a unit, it's just a number. Mass has a base unit of kilograms. And then we have speed squared or velocity squared. Now, obviously, if I'm squaring a quantity, I'm squaring its units as well. And we know that speed is in meters per second, or ms to the minus 1. So that leaves me with, let me just zoom in a bit. That means I have meters squared per second squared, or otherwise, like I said, kilograms meters squared s to the minus 2. And now I can check. Does this side of the equation, these SI units of joules match the SI units of Newton meters? Yes, they do. Let me just do that. Hence, my equation is correct. It's homogeneous. There's a lot of more examples that we can do, but I will leave that for class. Actually, I'll do one more, just for very quickly. Don't know if you remember the Suvat equations, which you will have to remember them very soon. That's coming in chapter 3. I will take one of them and we can analyze its units. So you have, let's use V is equal to U plus AT. I'm going to do a quick reminder here, a very, very quick reminder. V stands for final velocity, U stands for initial velocity, A is acceleration, T is time. So whether it's initial or final velocity, we know that velocity or speed have the same units, which is meters per second. Now we also know that U, which is the final velocity, is meters per second. But then we have acceleration. Acceleration, we already showed it above in the previous part. So we add, because there's an addition. There's no division, there's no multiplication in this part, it's addition, but there is multiplication between acceleration and time. The units of acceleration are meters per second squared. And you can do that easily with the equation as well if you're not sure about it. And we know that time has unit of seconds. So what I have is meters per second is equal to meters per second plus, when I do this calculation, so I have the same quantity, so s to the minus 1 times s will give me s to the minus 1, which matches every single one of them. Since I'm adding the quantities, then I will have both sides. So this is homogeneous equation. If, for example, I made a mistake in an equation and I tried to add kilograms to newtons, that wouldn't work because it just doesn't add up. It doesn't make sense for you to add, I don't know, mass and weight together. They don't have the same quantity, but it has to be homogeneous. Both sides of the equation have to come to the same base units, otherwise it doesn't add up. You do have to be very mindful that you will need extra work on matching certain symbols. So you are used to maths combining different numbers. So for example, if I gave you 10 to the minus 6 times 10 to the 5, you know how to treat indices, right? So you have to do minus 6, since you're multiplying the same base, you add the indices together, so with minus 6 plus 5, and then you have 10 to the minus 1. It's exactly the same thing I did here. We have the same base, and you're just adding the indices. So an s is the same thing as having s to the 1, s to the minus 2 times s to the 1, which is this case here, in case you're not yet very confident with your indices. That leads you to s2 minus 2 plus 1, which is minus 1. Just make sure that if you have any questions on that, you let me know, and we can go through it in class. You will have actual exam questions asking you to prove whether some equations are homogeneous, so please do practice with some of them as much as you can, especially with the derived units and their equations. We'll do some more practice in class as well. The next part is the SI prefixes, and most of you that I've taught already, you know how important they are. It's actually to make our lives a bit simpler. So for example, the smaller units are to make it simpler for us to see quantities. Instead of me writing, for example, 0.00000000012, I can write this number in a simpler way by using one of the prefixes listed here. Or instead of me writing 1.1500000000 and go on, I can write it simpler by just using one of these unit prefixes. So they're not here to make our lives hard, they're here to simplify our lives. And once you get in the flow of it, you'll find it very, very easy. So let's start with the actual ones that you do have to know for the course. As you can see, it says that you have to apply knowledge and understanding of prefixes and their symbols to indicate the decimal submultiples or multiples. Submultiples are the ones that make the number smaller, and multiples are the ones that make the units bigger. You know the most common ones. So when we talk about centimeters or millimeters, now the unit is the meters. The unit prefix is either the centi in the centimeters, so centi is the prefix, meters is the unit. That's why they call them prefixes. You do that in English as well. You have a word is like antimatter and matter. So anti is a prefix in front of the word to denote something else that word means. So it's quite similar in terms of calculations And in terms of keeping things nice and tidy in physics and in sciences in general, to denote extremely small things and extremely large things that we can measure but wouldn't look nice to have to keep writing in these ways. So I will start with the smallest quantity that you do need to know. It's pico, which is 10 to the minus 12. Actually, I'll make a nice table for that. Okay, so now I have the table ready. I will just simply, I'll actually start with the largest one. Even though it's not listed in the course, I will just introduce, it's not the largest that exists, by the way, but you could come across it during the course. So I just want to simply introduce it. Is Peta. That's the name of the prefix. It's a capital P. And it's a factor of 10 to the 15. Then we have tera. Don't know if you remember terabytes and things like that. That might be useful if you find that useful. That's 10 to the power of 12. That's the factor that you multiply any quantity by. You have giga, which is capital G, 10 to the 9. You should know this from your GCSE course. Mega, so the only new ones are these two so far. Mega, you should also know, is capital M, is 10 to the power of 6. Some people choose to remember it as 1 million because it is the same number. Kilo, with lowercase k, and that's 10 to the power of 3. Deci. Now, deci stands for 10 to the minus 1, lowercase d. Like decibels and things like that. You might have heard that before. Centi, obviously centimeters. You know that you have to divide meters by centimeter by 100 to get. You have to divide centimeters by 100 to get into meters, which is the same exact thing as saying 10 to the minus 2. Centis, lowercase c. Then you have milli, lowercase m, which is 10 to the minus 3. You also have micro. Now this is like a U with a line at the front. Is a lowercase Greek letter mu. That's 10 to the minus 6. Nano, lowercase n. I think the only symbol that you really, you need the prefix symbol that you haven't come across very often is micro, because it's a different letter to the English alphabet. So just get a little bit of practice with that. Try and just write a U letter and then just draw a line in front of it. That's the Greek letter, mu. Then you have nano, we said, 10 to the minus 9. Then you have pico, lowercase p. You see, this is lowercase p, that's capital letter P. 10 to the minus 12. And femto, which is the lowest one for your course, that might be mentioned in your course. Actually, femto definitely is mentioned in your course. Even though it's not mentioned here, which I'll go back to in a second, it does come up in nuclear physics, so you definitely will come across this. So this is why it's a list of symbols to know, of unit prefix symbols, I mean. So an example of what can come up. You might be told, for example, this comes across, like I said, nuclear physics. They might tell you that the diameter of the nucleus is, I don't know, 1.3, 2.3, let's say, femtometers, which is the order of magnitude of a nucleus. It's quite tiny. So instead of you having to write 0.00000 to 3 meters, you just simply write this number. And another way of seeing it is 2.3. You always replace the unit prefix by the factor times 10 to the minus 15. So since I already said this is the factor, and then you just leave the unit right next to it. So the unit doesn't change. It's the prefix that gives an essence of the actual size of that value instead of you having to write this whole number down, if that makes sense. This looks prettier, takes less time to write. This looks even prettier with less time to write. This takes too long to write and too much to think for. So it's a balance of things in terms of the units. That's why we use these units. Now, these orders of magnitude usually involve calculations on the nuclear level, sometimes including this as well. More likely these values come in terms of electrical units and, current or capacitance, which we're going to come across later on in the course in A2 content. It also very, very helpful when it comes to, for example, in calculations for waves, and so on. So we will come across a lot of ways that we're using that, and it will make more sense. And then we have the extremely big numbers, and you can guess right, this has to do with universe, and we will see it more used in much bigger things, or even with calculations, again with electricity, but in a different way, like the amount of energy we use, or so on. So you will see more examples of this being used, and why it's so useful. Instead of having to write really long numbers or really short numbers, it makes things simple. And once again, just like with the units, it's a common language across every scientific research done. It's a common language between scientists in general. Okay, so we have come through all of the content that I wanted to go through in this session. This is actually better coming across during a practical or even during some practice of exam questions. It's better to see in practice. But it's just basically simply labeling the graph axis and tables and columns in the right way, which you have seen in your GCSE, but it will be reinforced more and more the more we go throughout the course. It even mentions the fact that it's set out above in the other part. So I hope you understood most of this. If you have any questions, please write them down for lesson time. Thank you.